Good morning, everyone. Myself, N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So, in the previous module, we have seen the elastic buckling of thin plates and inelastic buckling of thin plates, and even we have seen the formula for the critical stress or the buckling stress in the elastic zone and even in the inelastic zone. Now, in this module, we are going to find out the experimental determination of critical load for a flat plate. Okay, and before we go into this one, experimental determination of critical load. So, experimental determination of critical load that you might have done in the aerospace structures lab, and wherein you'll calculated experimental determination of critical load by means of a plot called Southwell plot. Okay, so Southwell plot in which the deflection is to be plotted versus deflection by load. Okay, and then therefore through this we are going to find out the experimental determination of critical load. So in the aerospace structures lab, and you got the column, and then you got the column with different end supports and end conditions, like both the ends are hinged and both the ends are fixed. One end is fixed and the other end is hinged, both one end is fixed and the other end is free. So with these different end conditions for the column, and what you do is you just try to increase the load gradually, and you can observe the column that takes the deflection pattern, and therefore once the maximum load in that column is reached, then it is going to fail. So the before failure, whatever the amount of maximum load it carries, so that we regard as critical load. Okay, and therefore, so similar, we are going to extend the concept of the critical experimental determination of critical load for a column to a thin plate. Okay, so now here, so let us if you look at the learning outcomes in this module, so at the end of this module, the students are able to determine what is the critical load for the thin plate, and students are able to analyze the local instability in a thin plate. So what is instability, what is local instability, what are different types of local instabilities that are available. So, and then we are going to assess the instability in the stiffened panel. So the normal panel will be there, and we are going to see what is the stiffened panel and what are the instabilities that are occur in the panels. So the critical load for an actual rectangular thin plate is found in a similar manner, so to that of the column, by means of a Southwell plot. So just now we have seen the Southwell plot, that is nothing but what? The deflection is to be plotted versus deflection by load. Okay, so this is a Southwell plot. So in the column we have used that Southwell plot. So same concept here also, we are going to extend even for the thin plate also. So the displacement of an initially curved plate from the zero load position that is found in the previous unit, which we can assume it as W1, because initial deflection we can assume it as W0, that as summation m equals to 1 to infinity, summation n equals to 1 to infinity a mn into sine m pi x by a into sine n pi y by b. So this is the initial deflection you can assume, and after applying a load, a compressive load, and it is going to deflect further, and let us assume it has given, the deflection is given by W1, in which the unknown coefficient we have taken as Bmn, and even we have seen in the previous unit, the Bmn can be written in terms of Amn with this formula, that is Bmn is equals to Amn into Nx divided by pi square d by a square into m plus n square a square by mb square whole square minus nx, where nx is the compressive load in x direction per unit length that we have assumed. Okay, so now the coefficient Bmn increases with the increase of the compressive load intensity, that we can see from the diagram. So if this nx load increases, again the Bmn increases. So that is what is mentioned here, that coefficients Bmn increase with an increase of compressive load of intensity Nx per unit length. And when Nx approaches the critical value, that is given by Nx critical, the term in the series in the formula, it corresponds to the buckled shape of the plate and that becomes the most significant. So what is that? The term in the series. So whatever is there here, so this will become critical, and so that the buckling load can be predicted here from this one. Okay. So, and then for if you consider a square plate in which you can assume m equals to 1 and n equals to 1, which gives the minimum value of critical load, so that at the center of the plate you can substitute n equals to 1 and n equals to 1, and so for therefore A1, therefore W1, which is nothing but the change in deflection, you can get it as A11 into Nx divided by Nx critical minus Nx. So in the formula you can see here this one. So when you substitute m equals to 1 and n equals to 1, so you can write it as A11 into Nx, and Nx becomes Nx critical, the critical condition, that is. And then this complete one also, because it is the most important one, because a significant term for studying the buckling of plate. So therefore you can consider this as again Nx critical, and then you can write it as Nx, and therefore Bmn, that is, you can write it as B11, you can write over here. Okay. So therefore W1, you can write it as A11 into Nx divided by Nx critical minus Nx. And similarly you can consider W1, you can write in the other form also, as we discussed for Southwell plot, that is, the deflection should be plotted by deflection by load. So we are trying to arrange this equation so that you can write the equation as W1 equals to Nx critical into W1 by Nx minus A11. So where A11 is any unknown coefficient for the squared plate which has m equals to 1 and n equals to 1 more. Okay. So now the Southwell plot. So how do you determine experimentally? So you have to plot W1 versus W1 by Nx, where Nx is the load. So it is just like same like a column. So this is for the plate what we assumed, and whereas for the column the deflection should be plotted by deflection by load. So here W1 is a deflection, here delta is a deflection. So this is for the plate or the thin plate we have assumed, and this is for the column. Okay. So that is why we have seen in the starting that the concept of buckling of critical load of column, that will be extended to the thin plate. In the similar manner, by making use of the Southwell plot, we can determine experimentally. So when you plot this graph, and you can clearly find out the experimental determination of critical load from this plot. Okay. So now, so the graph is plotted versus W1 by Nx, and it will have a slope in the region of the critical load that is equal to Nx critical. And so this is the way we calculate the experimental determination of critical load, that is W1, it should be plotted by W1 by Nx, and from the plot only you can clearly find out the experimental critical load. Now the other one is instability and local instability. So that we have seen, there are local instability mean nothing but when you consider a plate, so it has got plate dimensions A cross B, and whenever you try to apply the loads, we have seen the example of two simply supported edges and two free edges, and whenever you try to load that plate, then it is going to deflect and it's going to buckle as well when the load is increased. So therefore it gives a certain kind of instability in the plate, so that it is important for us to study the instabilities. So in this, the local instability, there are two types of instabilities, that is the primary instability and the secondary instability. So usually we study these local instability as a primary and secondary by considering the slenderness ratio, and which is nothing but equals to slenderness ratio, and we usually depict by lambda, and it is defined as equivalent length of the column to the minimum radius of gyration. Okay. So this LE by R ratio is very important to define whether the instability is primary or secondary instability. So usually for LE by R greater than 80, so this type of column is considered as primary instability, and usually in the primary instability, what happens here is the plate try to buckle as a whole one. Okay, the complete plate. So there you don't find any changes in the cross sectional dimensions of the plate, rather the plate will fail as a whole unit. Okay, so that is we call it as primary instability. And in the secondary instability or the usual, it is called as local instability, in which the slenderness ratio LV by R, which is less than 20. So those type of plates we regarded as secondary instability or local instability. Now what happens here in this is, the cross sectional dimensions, you can observe there are changes in it. Okay, so whenever you try to increase the load, now in the secondary instability, you can find that the changes in the cross sectional dimensions will occur, and the wavelength of the buckle is order of the that cross sectional dimensions. Okay, and the third one is nothing but, if it's intermediate, the slenderness ratio is between 20 to 80. So the buckling usually occurs by the combination of both, that is primary instability as well as secondary instability. Okay, so these are the different types of local instabilities what we have, and you can see here, so the thin wall columns in aircraft structures usually in the shape of longitudinal stiffeners, which are fabricated from the extrusion process by forming from a flat sheet. So in this diagram you can see the variety of cross sections that are used for composing of a flat plate elements, and they are arranged as the sections like angle section and form channel, extruded Z section and top hat section, like this. Okay, so now if you see some examples, buckling occurs when the weakest placed element, usually a flange, reaches to its critical stress, and then for a flat plate which is simply supported on 3 edges and one edge is free, so these 3 simply supported and one edge is free. And when you take this example, and for example we assume the A by B ratio which is greater than 3, and which is taking the value of K, buckling coefficient, that is equals to 0.43, and if you assume elastic buckling, so that you can substitute neta equals to 1. So the critical stress or the buckling stress for this type of example, that is 3 simply supported edges and 1 free edge, and the buckling stress is given by sigma critical equals to 0.388 capital E into T by B whole square, and where in which the nu is taken as 0.3 for the example. So this is one condition. Like that, you can take different types of edges, and you can take the different values of A by B ratio, and you can take the different values of buckling coefficient K equals to 0 K, and therefore you can get the corresponding stresses, because we got the generalized formula, that is equals to sigma critical equals to K pi square E by 12 into 1 minus nu square into T by B whole square. So this is a general critical stress or the buckling stress formula. So you can, depending upon the different end conditions, different values of K and A by B ratios, you can get the critical stress formula. Okay, and coming to this one, instability of the stiffened panels. So in the previous session we have seen that the plate has to be stiffened on all the 4 edges, or maybe on the 2 edges depending upon the requirement, so that the buckling can be delayed and the strength of the plate increases. It can be able to take many loads than the normal plate. So usually the plates which are having the larger values of B by T ratio, so they will buckle at low values of critical stress. So an effective method of reducing this parameter is to introduce the stiffeners along the length of the plate, thereby dividing a wide sheet into a number of smaller as well as more stable plates. So a wide sheet, when you consider, so it can be divided into smaller number of many parts, so that each part is taken separately. That is, each part will have more and more stable. Okay, so the sheet may be divided into a series of wide short columns by stiffeners which are attached across its width. So in the former type of structure, that is longitudinal stiffeners, usually they carry part of the compressive load, while in the later types of structures the load is supported by the plate. So both methods of stiffening are combined to form a grid stiffened structure. So stiffeners in early types of stiffened panel, they possess a relatively high degree of strength compared to with the thin skin, resulting in the skin buckling at a very less or lower stress level than the stiffeners. So a more efficient structure is obtained by adjusting the stiffeners across the section, so that buckling of the buckling can occur both in the stiffeners and the skin at about same stress. So this is how this is achieved. This is achieved by a closely spaced stiffeners of comparable thin thickness of the plate. So when you try to arrange the stiffeners very closely in such a way that it will have a consideration like stiffener and skin can fail at the same stress. Okay, so this is nothing but what we have, instability of the stiffened panels. Again, the instabilities, again you may have local instability like primary instability and secondary instability, just like a plate. So here also you can have, but it will have a more values that the buckling can be delayed and the stiffened panel able to take more and more load than the normal plate. Okay, so since the stress is same in the skin and stiffener, so buckling occurs a unit between them, and there are various modes of buckling are possible, like primary buckling, local buckling that we have seen, and the prediction of critical stresses for the panels with large number of longitudinal stiffeners is difficult, and usually it relies on the semi-empirical methods. So this is the stiffened panel. We can see that a wide sheet has been supported by stiffeners, usually in terms of columns like this, where you can consider the total width of the sheet, and BST is nothing but the width of the stringer, and this is the TST is the thickness of the stringer, TSK is the thickness of the skin, and BSK is nothing but the width of the skin that is between the panels. Okay, so you may have different cross sections. So the column sections maybe you may have Z section, I section, top hat section accordingly. Okay, so it is possible for the panel to behave as a Euler column, and for these kind of columns. So when you consider the column, the Euler critical stress, as we seen here, that is pi square EI by LE11 square, which you can write in terms of slenderness ratio. So if the column is failing like a Euler model, then the Euler critical stress is given by sigma critical equals to pi square E by LE by R whole square. And then, for example, if the buckling stress, that is in addition to the column buckling, if the individual plates elements comprising the panel cross section, they may buckle as long plates. So in such case, you can take this as critical load as N.Uday into K pi square E divided by 12 into 1 minus nu square into T by B whole square, and where the values of K, T and B that depend upon the particular portion of the panel being investigated. Okay, and for example, the portion of the skin between the stiffeners may buckle as a plate, and which is simply supported on all four edges, and for that case you can assume A by B ratio greater than 3 and K you can consider it as 4. So therefore the critical stress that is given by sigma critical equals to 4 pi square E divided by 12 into 1 minus nu square into TSK by BSK whole square. A further possibility is there, that is the stiffeners may buckle as long plates which are simply supported on 3 sides and one edge is free. In such case, you get the critical stress as 0.43 pi square E by 12 into 1 minus nu square into TST by BST whole square. Okay, and the compressive load is applied on the panel over its complete cross section. So the compressive stress taken as sigma A, that is equals to Nx by T bar, and where Nx is the load per unit length and T bar is nothing but the equivalent skin thickness, and it is given by T bar equals to AST, area of stringer, divided by width of the skin plus thickness of the skin. So this equivalent thickness is very, very important, and you can substitute over here, you can get the compressive stress. Okay, and where here AST is the area of the stiffener. Okay, so further types of instability that found in stiffened panels, so they occur where the stiffeners are riveted or spot welded to the skin, and such structures usually they are susceptible for inter-rivet buckling, and where you can observe the wrinkling of the plates that will arise in the plates, and usually in this type of wrinkling whenever it happens, so the wavelength of the buckle is greater than the rivet pitch and the separation of the skin and stiffener does not occur. Okay, so that's it from the today's session, that we have seen local instability, that is instabilities of stiffened panels, and then followed by the determination of critical load. Okay, so let's meet in the next session with the other topic. Thank you.